Is the planet literally tearing itself open beneath the waves? Could sleeping giants of molten rock under the ocean suddenly awaken and rewrite coastlines? And if the seafloor is indeed loading with magma and stress, who should be watching, and how fast should we worry? Those questions make for viral headlines, but the real story is both subtler and more spectacular. Earth's interior is continuously rearranging itself by means of predictable physical processes that, when combined in particular ways beneath the ocean, can produce anything from slow seafloor growth to true super-eruptions. What follows is an investigative, technically focused explanation of those mechanisms: the mantle drivers, plate interactions, magma chamber physics, hydrothermal interplay and caldera behavior, with special attention to systems nearest the United States west coast, where divergent ridges, transform faults and a dying subduction zone conspire to create a dynamic, sometimes volatile, seafloor. The sharpest way to begin is to set the scene in physical terms. Imagine the lithosphere, Earth's rigid outer shell, as a mosaic of plates floating on a convecting mantle. Where plates diverge, new ocean crust is made. Where they converge, one plate dives beneath another. Where they slide past, strain accumulates and is released in transform motion. Beneath all of these motions lies heat, not heat as in a domestic furnace, but in the form of buoyant, partially molten rock and the thermal gradients that drive melting. Where that heat focuses, magma will form, collect in reservoirs, and eventually seek pathways upward. The geometry and chemistry of the plumbing, the force balance between magma pressure and the surrounding rock, and the presence of water together determine whether eruption is gentle and effusive or explosive and catastrophic. At mid-ocean ridges, tens of thousands of miles of underwater mountain chains knit the ocean basins together. There, the mantle rises, decompresses, and partially melts, producing vast quantities of basaltic magma that create new sea floor. This is the site of most of Earth's volcanic output by volume. The eruptions here are typically low viscosity and effusive. Lava extrudes under cold seawater and forms bulbous pillow flows because the molten rock chills instantly against the overlying water. The critical point for understanding why most ridge volcanism is not explosively dangerous is pressure. Water depths of thousands of feet put great constraint on volatile exsolution and fragmentation. Nonetheless, even at ridges, the physics are complex. Magma supply varies in space and time, leading to cycles of inflation and deflation of summit areas, episodic fissure eruptions, and rifting events that transfer strain along the ridge axis. Axial volcanoes along the ridge axis episodically inflate like balloons as melt intrudes into shallow chambers. When the chamber pressure exceeds the tensile strength of the overlying rock, a dike propagates and an eruption begins. The process is mechanical. Chamber pressure minus lithostatic load and tensile strength governs failure. Off the North American west coast, the Juan de Fuca and Gorda spreading centres and their array of seamounts are the most direct expression of this ridge process. There, seafloor volcanoes, such as large axial calderas, periodically fill and empty in cycles driven by magma recharge through the upper mantle and crustal intrusion. The magma that collects in these shallow reservoirs is often basaltic and relatively hot and volatile poor compared with the silica-rich magmas that feed continental supervolcanoes. Basaltic systems tend to erupt fluidly, but they can still produce powerful seismic swarms and rapid deformation when magma moves. When we say a submarine volcano is loading, we mean that magma is accumulating and pressurizing a chamber. The observable signals are uplift, tens of thousands of small magnitude earthquakes, and changes in hydrothermal discharge chemistry. Those signals are unmistakable to modern arrays of seafloor seismometers, pressure sensors, and deployed cables. A second key mechanism is subduction and slab dynamics. At convergent margins, oceanic lithosphere bends and plunges beneath an overriding plate. The descending slab carries with it a hydrated crust and sediments. As the slab descends, it progressively releases water into the overlying mantle wedge by metamorphic dehydration reactions. That water lowers the melting temperature of mantle peridotite, generating magmas that feed arc volcanoes. The classical view ties arc volcanism to this water-induced melting and to the geometry of the slab. Yet slabs are not immutable. They can tear, break, and fragment. When a slab tears, it can form an opening, a so-called slab window, through which hot asthenospheric mantle can upwell directly beneath the overriding plate. The thermal and compositional consequences are profound. Hotter, potentially more primitive magmas can reach shallow levels, and areas that were formerly magmatically quiet can become loci of new volcanism. This slab window physics is relevant to the Cascadia region of the Pacific Northwest. There, parts of the oceanic plate appear to be fragmenting as the plate's geometry adjusts to changing boundary forces. A fragmenting slab reduces the downward pull that sustains subduction, and the resulting thermal anomaly can facilitate unexpected magmatism inland. In mechanical terms, slab tearing changes the balance of forces. Slab pull diminishes, asthenospheric upwelling increases, and the overriding lithosphere responds by tensional cracking and localized melting. Over geological timescales, this can produce microplates, novel volcanic centers, and even back-arc spreading, a rearrangement rather than a sudden rupture of the crust. Turning to the phenomenon of submarine super-eruptions, it is crucial to define what super means in volcanological terms. Super-eruptions are characterized by eruptive volumes, typically an order of magnitude greater than historic large eruptions. The thresholds commonly start at tens to hundreds of cubic kilometers of erupted material. On land, examples are rare but dramatic, caldera-forming events that evacuate vast magma reservoirs. Under the sea, the physics are modified by water pressure and hydrothermal exchange, but large caldera systems do exist and have erupted catastrophically in the geological past. The presence of water can both tamp explosions by confining gas expansion and enhance explosivity when magma and water interact violently at shallow depths. The interplay depends on water depth, magma volatile content, and the speed at which the reservoir fails. Consider a large submarine caldera lying under shallow water. If a silicic magma body accumulates over tens of thousands of years, exsolving gas and building overpressure, eventual failure can lead to a caldera collapse and eruption of a magnitude comparable with the largest continental super-eruptions. If the chamber breaches at depths where water can flash to steam and physically fragment the magma, you can have highly explosive interaction generating fine ash, pumice, and widespread tephra dispersal. The difference between an effusive mid-ocean ridge eruption and a submarine super-eruption hinges on magma composition, volatile budget, and depth. Hydrothermal alteration plays a subtle but critical role in this story. Seawater that percolates through the hot crust becomes a reactive agent. It dissolves metals, alters rock mineralogy, and lubricates faults. Chemically altered rocks are mechanically weaker and more susceptible to failure under stress. Moreover, hydrothermal systems are conduits for heat loss from magma chambers. The efficiency of that cooling controls how long a chamber can accumulate melt at high pressures. In places where hydrothermal circulation is vigorous, the thermal budget of shallow magma bodies can be damped, delaying the progression to super-eruption conditions. Conversely, in systems where hydrothermal outflow is restricted, heat can be trapped and pressure can build more effectively. In addition, hydrothermal fluids transfer volatiles and alter crystallization paths, affecting magma viscosity and gas retention. Another important mechanical element is magma chamber pressurization and roof failure. A chamber pressurizes as melt is replenished or as gas exsolves from crystallizing magma. The pressure state of the chamber is bounded by lithostatic pressure, the weight of the rock above, the tensile strength of the host rock, and the presence of pathways such as faults and fractures. Failure can occur when chamber overpressure surpasses the tensile threshold and a dike or vent opens. The propagation of that dike depends on the local stress field and the chamber's internal pressure distribution. In some systems, incremental failure produces slow, repeated eruptions. In others, catastrophic roof collapse leads to caldera formation and massive eruptive pulses. The geometry of the chamber, the presence of multiple interconnected reservoirs, and the viscosity contrast between crystal-rich and crystal-poor magmas control the style of failure. Caldera resurgence is the mirror process. After a caldera collapses, renewed magma input can uplift the caldera floor, forming resurgent domes and repressurizing the system. This cyclical behavior, accumulation, failure, collapse and resurgence, can repeat over tens of thousands of years. Each cycle reconfigures the shallow plumbing and can leave a complex stratigraphy of ignimbrites, lavas and hydrothermal deposits. Submerged calderas record these cycles in sedimentary layers and structural geometry. Modern geophysical imaging reveals stacked intrusions, ring faults, and resurgent domes beneath many big calderas. When we place these generic mechanisms in the context of the US West Coast and adjacent offshore regions, the portrait becomes concrete and regionally important. The Juan de Fuca and Gorda plates are young oceanic plates being subducted beneath North America. The geometry of the plate boundaries here creates narrow corridors where mantle upwelling, slab dehydration, and transform motion interact. Spreading centers such as the Juan de Fuca Ridge supply basaltic magma to axial volcanoes that routinely inflate and erupt. Transform faults, such as the Blanco Fault, create additional sites of shear heating and localized fracturing that can channel magma. Those faults are mechanical discontinuities. They concentrate strain, create permeability for fluids, and can interact with magmatic systems to trigger or redirect eruptions. In Cascadia, the interplay of slab dynamics and near-ridge volcanism creates a hybrid hazard landscape. The overriding plate hosts both arc volcanoes and volcanism related to slab windows. If the slab tears, the upwelling asthenosphere beneath the gap can produce more primitive magmas and increased volcanic flux. That process does not mean that the crust will split open in a human lifetime. Rather, it signals a long-term reorganization. Still, during episodes of enhanced magmatic intrusion, local seismicity and deformation can escalate rapidly over months to years, producing observable patterns that modern instruments readily detect. The key is that these signals allow scientists to forecast probable eruptive behavior on short timescales for individual volcanoes, even while the regional tectonic evolution plays out over millennia. The physical processes that lead to a true submarine super-eruption require a specific confluence. First, a large, evolved magma body must evolve in the shallow crust. This commonly implies high viscosity silicic compositions that can trap gases. Second, the volatile budget must be sufficient so that when failure occurs, gases expand violently. Third, the chamber must reach a state where roof integrity can be suddenly lost, either by tectonic faulting, magma overpressure, or external triggers such as large earthquakes. Fourth, water depth must be shallow enough or the mechanism of interaction oriented so that magma-water interaction enhances fragmentation rather than simply quenching the eruption. When these factors align, a caldera-forming event can occur under the sea, and such events are known from the geological record. Historic and geologic cases show the range of outcomes. Some submarine eruptions are purely effusive, reshaping the seafloor without fanfare. Others have breached the surface, creating temporary islands or explosive plumes. And a small number in Earth's history have reached the scale of super-eruptions. The difference is not magic, but mechanics, composition, depth, pressure, and tectonic setting. In short, submarine systems are capable of major explosive behavior, but that capability is constrained and in many places limited by the very weight of the ocean above. From an investigative perspective, modern monitoring changes how we interpret loading signals. High-density seafloor-cabled observatories, autonomous underwater vehicles, and improved seismic tomography let us see magma migration, magma chamber inflation, and changes in hydrothermal chemistry in near real time. That observational ability transforms vague rumour into testable hypotheses. Is a swarm of earthquakes migrating upward along a dike? Are seafloor pressure gauges recording uplift? Is hydrothermal vent chemistry trending toward more reduced species that suggest new magma ingress? Put together, these data streams let volcanologists assign probabilities to outcomes and better understand the physical controls on eruption. For West Coast residents, that means awareness supported by science rather than alarm. What then of tsunami risk? Submarine eruptions can generate tsunamis if they involve rapid displacement of large volumes of water, such as from flank collapse, caldera collapse, or explosive fragmentation that lofts mass. But the physics again limit the frequency of such events. Deep eruptions, even if violent, tend to vent energy into the water column without the coherent mass movements that create large tsunamis. Conversely, shallow catastrophic collapses can do so. Therefore, the tsunami hazard from submarine volcanism is highly context-dependent. The depth, the rate of mass movement, and the proximity to the coast matter more than the mere occurrence of an eruption. Finally, returning to a conceptual synthesis. Earth is not splitting in the dramatic cinematic sense, but its internal processes of mantle convection, plate motion, slab tearing, and magmatic pressurization are continuously reshaping the lithosphere. Where these processes concentrate beneath the ocean, the outcomes span a spectrum from slow seafloor construction to localized explosive disruption. The West Coast is neither immune nor extraordinarily special. It sits at the intersection of mid-ocean ridges, transform faults, and a complex subduction history that together produce a particularly instructive natural laboratory. The scientific narrative is not one of impending apocalypse, but of forces that operate on multiple timescales, seconds for seismic rupture, months to years for magma intrusion and eruption cycles, and millions of years for plate reconfiguration. For those who watch the charts and seismic webs, the lesson is empowerment. Geological systems give off measurable precursors when magma moves and pressure builds. The combination of seafloor monitoring, Remote sensing and numerical modeling means that geologists can often describe the mechanics of an event while it unfolds. That does not mean exact predictions of every eruption are possible. The natural world retains stochasticity. But mechanistic understanding of mantle plume buoyancy, slab pull and tear, magma chamber pressurization, hydrothermal feedback, and caldera collapse and resurgence turns sensational questions into tractable science. And for communities on the West Coast and around the Pacific Basin, this mechanistic clarity is the best guard against unhelpful panic. It gives planners, emergency managers, and the public a factual basis to assess hazard and resilience. So, when the seafloor rumbles and when a submarine volcano is loading, the story is not inexplicable doom, but a sequence of physical processes that scientists can read, model, and often forecast. Magma collects where mantle dynamics and plate kinematics permit. It pressurizes until mechanical thresholds are surpassed. It uses pre-existing faults or creates new dikes to reach the surface. And the eruption style is governed by a combination of magma chemistry, volatile content, and the surrounding pressure regime. In some rare cases, these processes culminate in caldera-forming events of super-eruption scale, whether on land or beneath the ocean. But those remain exceptional in the tapestry of Earth's continual internal remodeling. The planet is active, dramatic, and sometimes destructive, and understanding its mechanics is the only reliable path to both appreciating and preparing for its power. If you found this deep dive into Earth's inner workings enlightening, don't keep it to yourself. Like, share, and subscribe to stay connected with cutting-edge insights into our planet's most powerful forces. Your support helps bring more science-driven stories to the surface and ensures you won't miss the next seismic update beneath our feet.